So let me just make this picture again here. So we have f of s okay. So when we are designing two loops, so what was the thing? Like we did a PID controller here, right? We had a KD theta multiplied, and you had a theta reference here, right? So theta reference plus minus KD theta S. So basically, and this multiplied by a KP theta here, right? So that was the loop. So the objective is to, whenever we design two separate, now we want to design a PID loop for this. So we need a bandwidth separation, how fast these loops are working. So this loop works much faster than the outer loop, which is, so that means the theta changes in theta will be much faster than, so that we can have this loop separation. So what happens, so if this is faster and if this is slower, so when that means at this speed the S will be kind of 0 for this. Okay, the frequency at which this operates for this will be like approximately equal to 0. So for that, this whole thing can be replaced by K theta DC, because at the frequency with the other loop is operating, the other loop will already be settled down. So you said, okay, give me this theta reference. That immediately gives you that kind of theta reference and multiplied by DC. So this whole loop for designing this can be considered just as K theta. So that's the final value theorem, right? That's the final value of, so the idea is, okay, when we have theta reference going in, this whole loop can be replaced by K theta DC. That means, and then this goes to the other loop, which is G minus, what is that, LS squared by S squared, where I'm getting Z of S. So this is what we have. This whole first PID loop for between theta and F, because it is much faster, it's operating at a much higher frequency. That means, and because this is operating at a lower frequency, when we are dealing with this, you can approximate the whole thing by just, and it's saying immediately, you give a theta reference, the output is K theta DC multiplied by theta reference. So that's immediate, yes? Yes? We are designing it, right? I'm designing that when we choose, if you remember, we chose an omega n for designing the PID loop for the first loop. So it was, let's say, 4.4. Now when I design the second loop, I'm choosing that omega n to be 10 times less than that frequency, let's say. So purposefully that separation has been maintained. And you will see also an example in UAV also, right? So for example, the UAV, when it has to turn its heading, it has to change its heading, right? So it rolls first. When it rolls, its heading changes. So what do you think must be faster? This roll should be faster, or this heading change should be faster? The roll, right? It rolls kind of immediately. But like say you have to change 10 degrees of heading, it might take 2 or 3 seconds to change the heading. But roll changes immediately. So that's our design. That we are choosing that separation between these two loops. So that we, any other questions? That was a good question. So yeah, that's purposefully we are choosing because we have that, we can choose a desired transfer function, right? So the desired transfer function means we can choose how fast it responds. What is the natural? Okay. So under that assumption, we have a new. So now we can design a PID for this, right? So it will be simple now. We can. What we can do is, for this transfer function, again we can take, so we want to control Z reference now, so we have a Z reference coming, positive, negative, so this Z reference going from here to here, so that gives me an error multiplied by KP Z, right? And then I have, we can also take a derivative of that, so S into KDZ, we can add plus minus here. So basically, so these are the two, so KDZ and KPZ is what we need to find out now, right? So now next step is getting a transfer function between ZR to Z. Okay, so see what is happening here. What will happen is, from this we will compute what is theta R required, because theta R is the input, and that theta R will be input to the first PID loop that we designed. Okay, but here we are assuming that it's immediate, K theta DC multiplied by that theta R. Okay, so again, all we now need to do is find a transfer function between Z to ZR. Okay, so that's the objective here, and let's get started on this. So that's find the transfer function. That's the objective. Find the transfer function. So I did find the gain and I applied it to my inverted pendulum. Maybe it works only for a second or something, but I think you guys will be able to fix it. But that's my today morning's 30-minute rush to implement it. I'm sure I will be able to fix that, but questions here, what we are doing here? Anybody? So that PID loop is still there, but it is approximated by that just final gain. Okay. So how do we go about it? We just compute this. So let's see. So G minus LS square multiplied by S square into this whole shebang, right? So that is K theta DC multiplied by error, and that is KPZ into Z reference minus Z, and then minus KDZ into Z, right? And that whole thing is equal to Z. That's what we get out here, right? So this whole thing, so this thing is equivalent of what we are getting here, right? The term, so this is the term. So the error multiplied by KP, your SKDZ is, oh sorry, I need to multiply S here. Okay. So now, once this plug-in, all we now do the algebraic manipulation and try to find the ratio of Z versus by ZR. Okay. So let's see. So I can multiply S square with Z, so it becomes S square Z equals to K theta DC. So KPZ ZR minus KPZZ minus S KPZ into Z. Okay.
So now we can multiply k theta dc everywhere. K theta dc, kpz, z reference minus k theta dc, kpz, z minus ks, k theta dc, k dz, z equals to s square z. Okay? So now the idea is like we have one z reference term, right? And we have this, 2, 3 of z terms, just segregate. Yes?
What happened to the G minus LS? Do I understand? We multiply by S squared.
Oh yeah, this whole thing is multiplied. Yeah, good. Sorry. Nothing happened, I forgot. G minus ls square. Right? So yeah, that's good. We still, so let's go and multiply that also. So now we have G minus ls squared, right? So what we can do is multiply this and bring it this side. So we have, both are negative, right? Negative, negative. So it will be positive. It will be plus s square z. So we can take it outside. So it is k theta dc kpz plus s k theta dc k dz whole thing z equals to z reference, and z reference is again multiplied by g minus ls square k theta dc and kpz. Okay, so now good, we can take a ratio now. Z over zr will be equals to g minus ls squared multiplied by k theta dc kpz divided by s square plus g minus ls square into k theta dc kpz plus s k theta dc k dz. Okay, so that's the transfer function. We can do some more simplifications, right? Because we can get now, so the next idea is to separate between s square coefficient, s coefficient, and constant coefficient. So so we can do that. Basically, I'm more interested in a denominator because that's what we compare to choose the gains, right? So we have s square term here, s square term here. So s square will be, if I take s square outside, s square, so g k theta dc kpz, lot of bookkeeping here, plus s into g k theta dc k dz, and then minus ls square k theta dc kpz minus ls cube. So see the issue here, we have somehow the transfer function was like that, and we got a s cube termed here, because we're multiplying ls square here, ls cube k theta dc and k dz, right? This whole thing is like denominator, whole thing. So now the biggest coefficient is s cube. So you can now segregate it. We can have, so that denominator is equal to minus ls cube k theta dc k dz, and now s square terms are this. So s square term will be 1 minus ls squared k theta dc kpz. Just stop me because I cannot look at you while I'm writing this, so if I mess up with something, just let me know. KDZ, good, that's S squared. And then we have S term. S term is S, do you have any other S term? This one term, right? So S into G, K theta, DC, K dZ. And then the constant term. Constant term is, where is that? This one. So that's G, K theta, DC, KPZ. So that's our denominator, like whatever we have, there's some numerator and we have a denominator here. Good? So now a question is, how do we choose our, what should the closed loop look like? So what we can do is, because how many poles will this have now? The 3, right? Because it's a third order equation. So what we can do is choose something like S square. So our desired characteristic equation can be some pole S P1, right? And then standard second square S square 2 zeta omega ns plus omega n square, right? So that's what we can choose, and so we can choose a pole P1, let's say P1 equals to 0.5. Just it has to be in the negative half of the S-plane, 0.5, and then we can choose omega n z to be omega n theta. So remember last time we chose an omega n theta, so we can make it 10 times slower than the, so omega n z will be omega n theta divided by 10. So we want omega n to be 10 times slower than, so the standard rule is between 10 to 5. So let's say we choose omega n z here to be 10 and zeta to be 0.707, right? So in doing so, so when we plug this in, right, all these values here, we'll get an equation like S cube plus A1 S square plus A2 S plus A3, right? After plugging this, we get this equation. Let's say we will get a numerical value for A1, numerical value for A2, numerical value for A3. And the idea is now to compare this with this equation, okay? But of course, first you have to divide the whole thing by this coefficient of S cube, which is minus L K theta dc K dz. If you divide the whole thing, so that we can do is S cube plus 1 minus L S, this S square should not be there, L K theta dc K dz divided by, what is that, L minus L K theta dc K dz into S square. Similarly, we have G K theta dc K dz divided by minus L over K theta dc K dz into S, and then you have this G K theta dc K pz divided by minus L K theta dc K dz. So now we have coefficients, right? So our A1 will be equal to this, right? A2 will be equal to this, and A3 will be equal to this. So once you, so you have 3 equations and basically 2 unknowns. So we can compute. So your A1 equals to 1 over L K theta dc K dz divided by minus L K theta dc K dz. So basically equate these 3 coefficients and solve for Kp and KPZ and KDZ. Okay, so that's the whole idea. When I was doing today morning, what I did, somehow my equation I might have done an error and I got a S square equation, and that's why my pendulum is not working, I believe. So we kind of fix this problem here. So you got the idea what we, so then once you compute KDZ and KPZ from here, how would we implement our controllers? That's the idea. So KPZ and KDZ will come here, and we had K theta P and, KP's theta and KD theta from previous loop, right? So in your controller, in your controller file, you can have a control, and your S function is giving us theta dot, Z and Z dot, right? All the four states are given by the S function, right? So this is how you will implement. The first loop will be theta, you compute for theta reference, and theta reference is given by KPZ, which will be Z reference, whatever reference you want your cart to be converged to. So Z reference minus actual Z, which is coming from here, minus KD Z into Z dot, which is coming from here. Okay, make sure when this is in time domain. When we are doing in time domain, you don't take Laplace of Z dot. It exactly go to, so you ignore that S term. Okay, so theta reference comes from here, and once you have theta reference, you go and compute the force, which is our force equals to K theta Z, which is multiplied by theta reference. So this goes in here now. The output of this PID, which goes in theta reference, that's why I'm saying it successive loop closure. So you close this loop, you compute theta R, and this theta R goes to this, minus, this is KP theta, KD theta multiplied by theta dot. And this force then basically goes to that your X dot equations that you have, or this is equal to U. Okay, so got the idea what successive loop closure. So this is all like implementing is simple. How you computed KPZ, KDZ for gains was kind of messy, but implementing is simple. This is theta reference, and the theta reference goes as an input to the second loop, so that you can derive this error to 0. So the objective of this to make this error go to 0, right? ZR minus Z. So Z goes to Z reference. So for that, whatever theta is there, and then you want that error to go to 0, so that and compute an F which will make that error to go to 0. So that's how. Input is still 1 to the system, but we computed that input in 2 different loops basically. Any confusion? Any questions? So if I want to summarize this whole last week and a half stuff, maybe I should write it down, but if I have to summarize this, so what we are doing is you're comparing these coefficients, right? So A1 equals to this. So you know the value of A1, right? No. So not P term. So you multiply this whole thing, right? So P1 is what you chose. Let's say it's 0.5. And then this S squared 2 zeta omega n. So 2 into 0.707 into, let's say this is 0.4 because omega n was 0.4. So you compute these coefficient, multiply, then you will get a desired characteristic equation.
Okay, I understand.
Good. Okay. So yeah, that's the $1 million thing. How do I get a desired coefficient? So you basically start with, so okay, I want this system to be slower. So my omega n should be 10 times less than the previous loop, zeta 0.707. And that pole we can play with saying, hey, let's put it in minus 0.5 or something. And okay. We still have 20 minutes, so we'll jump to the autopilot thing now, if we don't have any further questions. So next week is spring break, right? Okay. So what I have done, like some, I think, have you seen? I have divided, I have provided topics for each project now. So what we have done is we have created modules. Maybe I should show you before we jump there. And maybe tonight I will put the objectives and rules for each project. So we have created 4 different modules. All the project related things will be posted in the modules. And basically I will create group assignments on like weekly activities you have done regarding the project, so that you don't get or I don't get surprised, or you don't get surprised at the end here. So everybody knows their team numbers, right? So if you see, there are 4 different modules, right? So final project 1, so if you go to this is, I think, sale. So team 1, 5, 9, 13. So that is sailboat simulation, modeling simulation and control of a sailboat. Okay. So everybody knows their team numbers? Anybody here? And I think there was one team who's one of the candidate is out, is no more in the class. I'll reshuffle that. And so basically the idea will be like, we will be helping you. Like this project is like I'm not testing you, or you don't have to figure things on your own. If you are stuck, just come and ask. And so the first objective is getting the equations of motion, or what are the objectives. So I think I will lay out the objective, at least general objectives, and then the team goes out, finds the best paper or in the literature. How do you actually model a sailboat? For example, what should be the equations of motion of a sailboat? So we as a group can find relevant paper that we want to implement. It's okay to take material from internet, at least equations of motion. Okay, but when you present it, we will be asking you a question how. Okay, so it should make sense to you guys. You should understand how it is derived and what each term means and things like that. So I think 60 to 70% of your grading in project will be modeling, because this is a modeling and simulation class. Modeling, can we capture the equations of motion and then actually implement it in MATLAB as function and all those aspects of creativity and things. So sailboat will have both hydrodynamics as well as aerodynamics involved in it, right? Because your controls forces will come to the wind pane, and the hydrodynamics will provide you drag and everything. So we have to figure out the equation for that. The second project is, I think, and I will. So to start with, I will put some relevant papers for each category. Say, hey, this is what I think is one of the papers that you should look at, and then you can come and discuss with me whether this is implementable, or we should find another paper, or if we can make some simplifications or things like that. Okay, and then if second project is team 2, 6, 10, 14. So this project I think is okay. So if you look at these modules, it will be clear, but so these are the topics. So second topic is modeling, simulation and control of aerially towed cable system. Okay, and I'm assigning these point of contact, like Melody will be a point of contact for the sailboat project. At least the questions can be addressed. And then modeling, simulation, and control of aerially towed cable system, Rohit will be the point of contact. And the idea is you're a big fixed wing UAV is flying with a rope attached to it or a cable attached to it with some kind of a drogue, right? So what happens, the idea is how should I move the UAV such that I get a desired trajectory for the drogue? So if I move the fixed wing UAV in a bigger circle, right, there might be a smaller circle here. If winds will be there, then this will be tilted because of the drag. We have a paper for it, and this will be easy. So the idea is, first of all, how to model. How do I get the equation? Simply without any control, if I move the UAV, so the UAV problem is already solved, right? You will be designing autopilot, so that part is already solved. Now you have to include the drogue equation so that what tension and drag and affects the mothership. Yes.
What's like a real life example of that? Just so I can like picture it.
Real life?
Yeah, like where does that system exist?
So this is a project called, so for example, let's say you are in a war zone or a place where you're flying smaller UAVs and you want to recover them. So it's called aerial recovery project. This guy goes, flies off, and because the speed of the mothership is much higher, and as the length of the cable increases, the speed of the drogue will be much smaller. So these other smaller UAV can come and attach to it. That's the idea. So it's an aerial recovery project. It seems hard, but it will be interesting. So, and the third one is towing an underwater vehicle. So you have underwater vehicle, you tow another simple tow fish kind of thing. So how the drag and currents will affect the towing? Can you actually control the position of the? And the fourth is landing a UAV, fixed wing UAV on a moving ship. So you will have, so airplane is already modeled, but you have to model the ship. Okay, and again, you will have to show, you have to divide that. Okay, you are responsible for equation of open UAV, you are responsible for the ship, you are somebody responsible for the controller. So you have to do some team management there so that make sure everybody works in the group. Okay. So please look at what teams you have, and tonight maybe I'll just post the rules and maybe the first papers to start with, what papers you should read, which will basically give you the, and then again, innovations, anything is all most welcome. Like if you want to innovate or be more, putting new, harder objectives for yourself, for your team, is great. Again, there will be 3 awards for the final project. Okay. So this will be fun. Again, so there is 2 more assignments. So this is the one I am posting, right? So you will be done for this assignment by Monday, right? And then 1 more assignment. We're done. No more assignment now. We're done with assignments. So this week, and then 1 autopilot assignment. That's all. And then we can focus on projects. Okay. Questions? So this is assignment 8 and assignment 9. That's, so you've already done 7, right? Submitted 7 assignments. So 8 and 9. And then we focus on these 4 projects, and again there is, the grading will be like, okay, it's not that if your controller is not working you will fail or something. No, that's not the case. Model, simulate, so you have step by step, and we'll give points for everything. Okay, your model was okay, you got 70% of it. Your controller was okay. Innovation or impress me, 5% of the grade kind of. So, okay. So now, let's get back to what is coming in next 2 classes. So
generally what we are doing is we have an open loop transfer function, right? G open loop or something, which is a transfer function. You're selecting an U for, and you're getting some state X. So there are a couple of things like, first of all, the idea is to track a reference output, or you can make it Y, right? Y. So you want to track a reference output. So basically you give a feedback, okay? So now you compute your output, which is, so this is negative, this is positive. So you multiply it with Kp. So your input is proportional to the error between the reference output and the actual output. And then to dampen it up, you also multiply by S. So you take a derivative of the output and add it here, plus, minus. So this is the PD loop that we have, and then you get a transfer function between YR to Y, basically, and that's the closed loop transfer function, okay? So closed loop transfer function versus open loop transfer function. So this PD controller is doing two things. First of all, it is taking your error to 0, right? And also it is your poles of the closed loop transfer function will be a function of the gains, Kp and Kd. So if you have a desired closed loop transfer function, you can compare their coefficients of the denominator and then compute Kp, Kd. Okay, so basically compare. So you have desired characteristic equation, right? The denominator. So desired closed loop, and you compare with your closed loop coefficients. Just compare coefficients, and basically you can choose your Kp and Kd. At least that will be the starting point of your gains. So that if everything is ideal, these gains should work. Then once you will see my response, and then you can go back and tune them. Here they might not be necessary because it's a simple system, but when we move on to UAV, you might need tuning as well. Okay, and what was the successive loop closure? You have two transfer functions. It's a product of two transfer function, basically your F. So basically F to theta and theta to Z, right? So you first loop close this loop with a PD controller, and then basically close this loop. No, not this loop, but close this loop. So basically two successive loop. But the idea is to separate the frequency. So the inner loop, which is this, must be faster, and the outer loop should be slower. So you can choose your omega n for the outer loop such a way that it is 10 to 12 or 5 to 10 times slower than the inner loop, so that the separation is there. Otherwise you will end up in problems. Because if I say give me this theta reference, and the theta reference also takes some time to reach, then that is not a valid thing. Okay? So that's the kind of, so you start with the open loop transfer function. So first compute the open loop transfer function. Simple. Okay? Ratios. Take a Laplace, find the ratios of input versus output. Okay? And then see what you want to do. You want to track a reference output. Then again, the next transfer function is between y to y reference. In that, your characteristic equation will be a function of both the p and both gains, PID or all the three gains if you are using integral gain as well. And then compare the coefficient with the desired characteristic equation. Means basically you have some desired poles that you want your system to be placed. And then you compute your Kp, Kd, and Ki. So that's the summary of a week and a half of material that we have covered. Questions? So the assignment will have two problems. One will be this. So you basically have to compute gains, put a controller in your existing simulation. That is the assignment one, you created these two simulations, right? So put a controller which gives an input that you feed in your S function. Okay, so in both for mass spring damper system and inverted pendulum problem. Okay, so I'll put more details in the PDF assignment, but these are the two problems. This time it's simulation. I want your thing to balance. Okay, so that should give you enough confidence to go forward with the UAV thing. Questions? Anybody? Yes.
So which of these values like goes with like a P term or a D term? Like the actual gain, like what values actually the coefficients?
We computed it, right? So you have, when you compare the coefficients, right?